So hi everyone, I'm Henry. I'm based here in ICCS, and I'm I work in kind of fundamental machine learning research. I work on something that's quite different to the sort of things that we've been talking about so far this week. I don't tend to touch neural networks. I focus on kind of models that are more closer to kind of statistical models, and there are various reasons why you might want to do that. And I'm hopefully going to kind of explain what these kind of fundamental differences are. I've only got an hour, so I'm kind of focusing on like very high-level ideas and kind of concepts. But hopefully you'll take at least that away from this. But please do interrupt if I'm sort of talking nonsense. But first of all, oh, these are my fancy slides. So who here would class themselves as a Bayesian already? 1, 2, 3. Okay, we've got 3. I'll keep note of this. Okay. So we have 3 Bayesians. Who do we have that's strictly not a Bayesian? Who very strongly is against the principles of the Reverend? Okay, no one. So everyone else is kind of indifferent. I don't know how many people there are in this room, but so not Bayes, we have 0. Okay, so I'll keep track of this as we go along. But before I begin, I want to kind of do a little, I guess it's kind of a very, very silly example. But let's suppose that we have some data here. So the data is going to be one-dimensional. It's going to lie on the x-axis, and we're basically trying to learn some sort of function that explains some response on the y here. So for example, if we had very simple data like this, we might think, okay, we've probably got a nice linear model like this. But what do we do if this is what we have? Do you want to come up, Paul? Draw a line through this data points? No, go on, off you go.
What am I doing?
Yeah, fit the model to that data point. But why? Why?
I have no idea. Like, why? Why?
So this is what I'm asking you to do. What sort of model, if I give you the single data point, what would you try and explain? How would you try and explain this? So you're drawing a straight line. Yeah. Why is that?
Because I have no idea what you want to do here. It's a single data point.
Yeah, exactly. So we're in a slightly precarious position, right?
Yeah, yeah.
It's very hard to pin down, but you could ask the same thing here. So even if I give you 2 data points, now what would you do?
So now I can draw a better line.
Yeah.
Like, why not? Now we've got.
So you're assuming that the data is going to look like this.
Yeah.
But what happens? Why do you not think it's something that's much more wiggly than this?
Well, I have no reason to, because I only have 2 data points.
Okay, so you're using something that isn't just in the data, right, to make that decision?
Yeah.
Okay, so you are a Bayesian.
Okay.
Yeah. But yeah, we'll revisit this later. But that's kind of the point here, is that there is much more to machine learning and statistics than just data sets. Okay, so that's kind of the motivation here. And kind of being Bayesian is the way to do this, I would say. But I'm kind of going to go through some examples here. It's going to feel very, very straightforward, hopefully. But the idea is to kind of get us thinking about the right sort of stuff. So this is kind of the standard way that we were talking about regression. So for me, any sort of neural networks, if you're not doing a classification problem, you're doing a regression problem. But neural networks certainly fit into this category often. Okay, so there's a tiny little bit of maths here, just so we get everything straight. But I'm going to say that I have some data. So I've collected n data points here. They should be the same n, but one of them's bigger than the other one. But ignore that. So I've got n data points, and my data points here consist of pairs of x's and y's. So in this setting here, the x's are along the x-axis, and we had the y's up here. Okay, but this is the sort of thing that we're doing here. So we're trying to learn a function that maps these x's to the y's, and we're going to try and use our data set to do that. Often we might already be aware that actually there's some sort of like noise in the data, so actually the data we observe is maybe the true function, give or take a little bit of jitter or something. So this is kind of the way we would write that. But this is kind of the key assumption here, is we're trying to learn some function that maps from some x's here to some y's. And these x's could be very high dimensional. They could be kind of one-dimensional like this, or an x could be like an image. So it could be like a matrix of pixels or something. But this is kind of the standard machine learning setting. But let's just start in this very, very simple model. So this doesn't feel very machine learning-y. but this is kind of where it all started. So this is the kind of the most simple model you could think of. So this is your linear model. Basically, the only things I need to learn now is this alpha and this beta. So I'm interested in, I've got some data. I need to pin down what I think my kind of intercept term is if I was going to plot the straight line, and also what is my gradient. Okay, so we've made this assumption that our model is kind of this linear model, and here I'm just plotting a ton of functions from it. Okay, so all I'm doing here is just generating random numbers for my intercept and my gradient. So you see that these are the sort of things that we're able to explain with our model. So at the moment, this is kind of my assumption. I've assumed that this model is probably good, and really any of these are kind of fair game. Okay, so this is all we've done at this point in the process. Okay, so now let's suppose we have some data. So we've observed this data here. Just for now, I'm assuming there's no noise involved, so these are kind of exact. So these are just going to be exact evaluations of my function, and I'm assuming my function has this linear form here. So it's very easy, kind of in a standard machine learning setting now, to define some sort of loss function. So here this is like RSS, or if you divide it by n, it'd be mean squared error. But this is some sort of measure of how bad or good my model is. And the idea is, can we kind of pick our function? So in this case, it'd be picking the alpha and the beta, so that this error term is as small as possible, right? And if we do that, we get a nice straight line that smashes its way through the data set. Okay, so this makes a lot of sense. We're in a setting here where our model is bang on, we don't have any noise, so it's kind of a very, very easy setting. But this is absolutely not what happens in real life. We have much large amounts of data, we're trying to model a much more wiggly function. This sort of matching here never really happens. So normally we'd probably be in a situation a little bit more like this one. So now all I've done is I've just added a bit of noise to the points I saw before. So you see we have this kind of error term at the top. And now the question is, let's again try and fit this straight line model. Okay. But in this setting, so I now know that there's some noise, right? And I could maximize my loss function, minimize my loss function, and all of these lines, give or take, I probably should have had a few more down here as well, give roughly the same loss. Okay. But if we kind of use the standard mechanism here, which is where we just try and get a single estimate of alpha and beta that minimizes my loss function, I'd only ever kind of return one of these lines, right? But now if we suppose that actually we're trying to make some predictions much further up, you see that kind of these small errors here that don't seem too bad actually get very, very large out of the data set. So it's very important to understand the spread. Oh, we've had a bad sample here. They're not lying in my, so it's very important here to actually understand how much uncertainty we have in the alpha and the beta. And of course, you can do that in these methods by kind of doing confidence intervals and bootstrapping and things like that, but you don't really see it very much. Another setting here is imagine that I've still got the same data, but actually I've picked a model that's a bit too complicated. Okay, and this is exactly what we do in neural networks. We have these incredibly complicated models, and we try and fit them to the data. But often we're in settings where, so if you look here on the top, we have alpha, beta, gamma. So we have 3 parameters in our model. In a neural network, we might have millions or billions of parameters, right? And typically maybe less data than that. So we're in a setting where we have got a model that's probably too flexible for the data. Okay, so this is the same thing as before. These are all kind of lines that roughly explain the data, but actually, if we don't kind of keep track of how much uncertainty we have in our parameters, it's going to be very hard to interpret the end result. And then here is an example as well with a neural network. Right, so these are all things. So I basically trained a neural network. I can't remember what it was, not a particularly deep one or a wide one. And I used some early stopping to stop it from overfitting to the data. So it kind of going through these data points and like this. But you see that, again, we need to keep track of our uncertainty in the parameters for this all to make sense. Okay, but the point is here that, yeah, fine, there are ways to do this with this setting. So what I could do is, yeah, kind of do some sort of stability analysis to perturb the my model parameters and see what happens downstream. But one of the nice things about a Bayesian framework, which isn't something I've explained yet, is that you kind of get all of this for free. But let's think about things a little bit differently. So before I jump into Bayesian machine learning, I'm going to do a very quick recap of kind of Bayes' rule and statistics. Hopefully a lot of you are familiar with this, but maybe some aren't. But let's go through this. So this is a very important formula, and it's basically a way of working out how much I can learn about something by observing something else. So let's suppose I'm trying to make some sort of claim about the probability of an event happening, a probability A. Let's go through a concrete example. So let's say the event A is suppose I've just turned up for lunch. I don't know anything about this lunch, and I'm trying to predict whether or not it's a free lunch. Okay. So I don't really know much about this. Based on kind of historical evidence, maybe I'm going to say, okay, maybe 1 in 10 of my lunches is free, which is quite a bold claim. Okay. But now we're going to say, suppose that we know something. So suppose we know B. So we've got A, I might have free lunch, but suppose we know B, where B here is, okay, so column is there as well. Okay, so column is the leader, the head of the maths department. You met him right at the start. But actually, he's at a lot of free lunches, I think. So now there's some interesting questions we can ask. So actually, I don't see column that often. Maybe I see him. Maybe I see him half the time I have lunch. That's probably an over-exaggeration, I guess. But what I do know is actually that given that it's a free lunch, the probability of column being there is very, very high. Okay. So basically, if the lunch is going to be free, column's going to be there. So these kind of pieces of information here are all we need to plug into the right-hand side of this equation, and we can now get a better estimate of whether or not the lunch is free. So before, all we could say, what was P of A? And that was 0.1. But now we can go, okay, suppose we are still interested in what's the probability that it's a free lunch, but now we know that column is there. Okay, and we can plug in all of our equations we've got, so we kind of get 0.9 times 0.1 divided by 0.5, which is 0.18 maybe? Yeah. So you see, just by knowing that column is there, I'm now twice as likely that my lunch is free. Okay, so this kind of stupid example here is what we're going to try and recreate in a machine learning problem. Okay, so now let's try and tie this in. Oh, already done that bit. Sorry, I'm playing around with this new slide thing and I've not quite got the hang of it yet. But now we're talking about, we're not just interested in what is the probability of an event. We're actually interested in what is the probability of seeing a function. Okay, so these are quite like complicated mathematical objects, and I'm not going to talk about the maths at all. I'm just hoping that we can kind of get some of the understanding. But I'm saying, okay, I've got some function. What is the probability of that function being the true function? Okay, so let's suppose we have some sort of prior over functions, and this is where we started. And then the question is, are we able to somehow get a more precise estimate of what this function is by doing something? And what can we do? We could collect some data. Okay, so we're now interested in what is the probability of this function given that I've observed some data. So this D here is the D I presented at the start. So this is like the data set that I've collected. Okay. So this is the purpose of kind of Bayesian machine learning, is that we kind of build things in this scenario. So we say, okay, this is what I think about the function already. And then my kind of best guess of the function comes from this posterior here. So this is what we call it. So we have a prior. So this is my information at the start. And this is the posterior. So this is the information that I have after collecting the data. And we can write this out using Bayes' theorem, which is the probability of D given F, probability of F over the probability of D. Okay. And we kind of proceed in this sort of mechanism, and I'm going to explain how this works in a minute. But this is kind of the key idea. So this is very different to the way that kind of standard machine learning works. So in standard machine learning, we had this very broad class of like all the possible Fs that we could have. So I showed you on the plot of all those straight lines, right, in a regression case. And we're just right, okay, which one of those Fs is the one that fits the data? And that's just what we did. Here, things are a bit different. So I'm going to define some sort of probability distribution over functions. So I'm going to say, okay, I think the function is probably a straight line, but it might not be. And then you don't actually fit the model. What you do here is you kind of do Bayes' rule. So you have this kind of closed form expression here. Sometimes it's not closed form, but often it is for the sort of models we use. And that gives us now kind of a new estimate of what the function should be given the data. So this is a very different mechanism to kind of the standard machine learning models. And I'm going to give you kind of more concrete examples of this now. But this kind of notion, I've explained that like we're interested in this sort of thing. So maybe some sort of prior of functions, like what does this even mean? This is kind of like a weird mathematical thing. Like a function is like a line, it's like an infinite dimensional thing. What does this actually mean? Okay, so let's return to the example from before. So now we've got, I'm assuming my function is this kind of alpha plus beta x, okay? Let's suppose that actually, well, what we're interested in here, oh, sorry, it's coming again, is working out a way, how can we define a distribution over functions? And that's a very difficult thing to do. But one way you could do it is as follows. So what I could actually do is just put distributions over these parameters, right? Well, unfortunately, we're missing a beta. There should be also a beta. Let's say that's also just to the right of it. So this here means that I'm saying I think my alpha has a Gaussian distribution with mean 0 and variance 0.1. Okay. So you see here that I'm putting priors, so like distributions, on these kind of alpha and the beta. So that means that this overall function f is now also a random variable. Okay, so I'm giving you some examples here. So now what I'm doing is I'm sampling from the alpha and the beta from these normal distributions, and I'm plotting the resulting f of x. Okay, so we're getting a picture that looks very, very similar to the one before, where we're just kind of getting these random alphas and betas, and we're getting these functions. The real powerful thing about thinking about things in a Bayesian way is that actually you can have much more informative priors. Okay, so this is basically the same picture as the normal machine learning setting, right? We're saying basically any f that's linear will do. But actually what we can do is if we know something up front, for example, if we know that actually the alpha and the beta are going to be very, very, very small, right? Then these now becomes the set of functions that we're interested in. Okay, so you can't really see any difference in these, right? We dramatically changed kind of the set of functions and the way we're attributing probabilities to these. Yes?
How do you assert the prior over alpha and beta without having a data point?
Without having a what, sorry?
A data point to inform you that they should.
Yes, so that's kind of, I'm going to come on to that, but that's one of the things about why this sort of setting, and this isn't what I'm advocating, this is kind of what people do in some settings is say, okay, I think I know something about alpha and beta, and you're right, that it's very hard to make those sort of abstract sort of things up front. But what we're going to get onto is actually in these frameworks you can say things, your prior could be like, oh, I think my function satisfies Maxwell's equations or something, right? So these are like things that we're using physics to make these sort of claims, right? And it's very tangible and you should be able to inject that knowledge into your learning procedure. But you're right, this is kind of feels quite arbitrary at this point. But I will kind of come around at the end to try and explain why we do care about this. But we can do another example here as well. So if you imagine now, we're pretty confident we think alpha is 0 up front, but we're willing to kind of concede that we don't really know what beta is. Okay, so we're allowing beta to be quite varied. So now this is kind of the set of functions. Well, these are the most likely options we have up front for our function space here. Okay, so here I've been trying to motivate how you can define some sort of distribution over functions. As I said, it's kind of quite a nasty mathematical concept. But the fact that you can sample from them, like I have done here, means that they are kind of real things that you can play with. But yeah, as you said, this is kind of still very kind of toy example. Does anyone else have any questions while we're here? No. Okay. So yeah, this ties back into your question that actually it can be quite hard to kind of specify the sort of information, like include the sort of information we want to include in this sort of framework. And that's why I'm going to talk about something called a Gaussian process, which is what I do most of my research on. But before I get there, I'm going to look at one quick example where this sort of thinking of kind of coefficients with priors on is helpful. So imagine that we have, we're trying to do some equation discovery. Okay, so we have some data, and we're saying, okay, I think my function is going to be something that looks like alpha 1 x plus alpha 2 x squared plus alpha 3 sine x plus blah, blah, blah. Okay, so imagine that I've kind of said, okay, I don't really know what my function is, but I want to learn something that's very interpretable. So I'm saying my function is kind of a linear combination of any of these possible functions I could think of. So I've got sine x, I could have e to the x, cos x. I could also include kind of differential operators in here. And we had an example the other day where they were looking at learning a differential equation, and they were looking at differentials up to order 8 or something, and he said there was 1,000 of these terms, right? So actually, if you did fit this model, you'd end up with 1,000 terms, and it wouldn't be interpretable. It wouldn't be a useful equation. But what we could do is using a Bayesian framework, and actually this is what the methods that he described do. You could say, actually, my prior here is that I want most of these alphas to be 0. Okay, so that is quite a useful prior to have, right? You're saying, I think there is a very kind of condensed representation of the underlying process here. I think it should really only have 5 terms in it or 4 terms in it. And so this is kind of one example where the sort of weird priors I discussed there actually make a lot of sense. So I want to say, yeah, I think that there is a very short expression that explains this data. So I'm going to kind of define a joint prior that makes sure that only a few of these things are active. So you'd have some sort of joint distribution over these alphas. So that's kind of one setting where these sort of things do work. Does this example kind of make sense to people loosely? Okay.
Just FYI, Henry, that's slightly below the minimum font size you can use on that board for the Zoom.
Ah, okay. Yeah, okay, I'll zoom out a little bit next time. Cool, right. So I've kind of introduced a few of these ideas, but the main thing is that the main difference between kind of the standard way to do machine learning and the Bayesian approach is that in the Bayesian method, we're including some knowledge that isn't in the data, and that can be immensely powerful, for example, in this setting here. Okay. But let's turn to Gaussian processes. So I've actually gone through this a little bit faster than I thought I'd do, so maybe I would have had more time, but I've kind of decided to do a very high-level overview of why people are interested in these things and the sort of problems that they can be applied to.
So,
okay.
I think I just want to sum up the previous part.
Sure.
So you assume some distribution for the parameters, and then you calculate how good this distribution is, considering the data available. Okay. Okay, thank you.
I'll have a concrete example in a second of like how it actually works, the updating. So at the moment, I've just shown you kind of, like different prior beliefs we could have about what the functions look like. So for example, I'm assuming that my functions are somehow sparse, or I'm assuming that they are linear, but they kind of, all focus on the origin in some way. So these are very like kind of specific things I'm saying about my function. But I will, in the next couple of slides, show you like how you actually include the data to kind of update that. But that's the main thing here, is that you're not just saying, okay, I've got a model, I've got some data, smash them together. Here we're saying, okay, actually we know some stuff. How can we include that in? And that's kind of, how the Bayesian methods work. And you will, I think more things than people realize are Bayesian when you kind of get down to a lot of the details. But yeah, this is kind of one of the most common ones. And how many people here have kind of come across Gaussian processes before? Ah, okay, loads. Okay, good. Okay, so this is going to be super, super trivial for all of you, I guess. But hopefully there's some interesting bits towards the end. But this is kind of a different way of defining functions. So I kind of showed you before that you can define things. We had this. Okay, and we were quite limited in this setting, right? Like we could put kind of priors on this and this, but actually it was quite hard to interpret. Like if I decide that alpha is going to have to be between 0 and 1, like what effect does that have on the functions? And so this way of viewing things is known as the weight space view. And this is where we're just interested in, like, can we put priors on the weights of our model? And this is very, very challenging to do. People have done this for neural networks as well. There are things called Bayesian neural networks, and that's where you basically put like a normal prior. Here I've got 1, 2, 3 parameters, but in a neural network, basically I have to put a prior on every one of my biases and every one of my weights. And actually fitting these models becomes very challenging just because of the scale. But it's very hard to interpret like why you're putting these priors on. Like what does it mean for like a weight in the middle of your neural network to have a Gaussian distribution? Like it doesn't mean anything. You don't know what that does to the function that comes out at all. And that's why I like working with Gaussian processors. So this is a different way of thinking about things, and I'm going to present them in kind of a function space viewpoint. That's what we call it. But the idea here is that we're actually thinking about the functions themselves. We're putting priors over like properties of the functions rather than on properties of the weights. And this is a much more direct way to kind of encode the sort of things that we're interested in when we're doing kind of like Bayesian physics discovery or Bayesian climate science. But here, this is kind of an abusive notation if you're familiar with it, but I just wanted to write this up just so we can kind of see what's going on. But here I'm saying that my function, so the prior for my function is going to be something called a Gaussian process. Okay? I'm going to kind of give you lots of examples of these in the next few slides. But the way Gaussian processes work is that you basically just specify something that's called a mean function, which you're going to kind of be introduced to in the notebooks in the next session. So I'm going to actually ignore the mean function bit for now. But the key thing for us here is this thing called a kernel. Okay. So this kernel, so that's in blue, and that's the thing that we specify, and that's the thing that's going to encode our kind of knowledge that we want to force into this algorithm. Okay, so this function, it's called a kernel, and what it does is it takes in two of our inputs, so two of our data points, and tells us how similar they are. And this feels like it's a very simple thing, and it is, and that's what's nice. But actually, by kind of messing around with this, you can encode some really interesting kind of physical properties. So it's very easy, for example, to force your function to be periodic and things like that. But I'm going to, I've got some really interesting examples of that. And when we go through the notebooks in the next session, you'll see much more of this. But let's start with this one. So this is something called the RBF kernel. There's a lot of maths involved in this, but I've decided not to include it. But what this does is basically, by choosing to use an RBF kernel, what I'm saying is that my function, all I'm saying is my function is infinitely differentiable, okay? Which sounds a bit complicated, but it just means it's super, super smooth. So these are all kind of samples from this prior, basically. I'm saying my function is infinitely differentiable. It could be any of these, right? And I could sample an infinite number of these functions, but here I've sampled 10. So we've got these kind of 10 very like smooth functions. And you see that this model here is super flexible, right? It's not like the linear one where it's kind of just the straight lines or the quadratic one. And it's actually better, the neural network as well. This is kind of more flexible than the shallow neural network I showed you. So here, this is what I'm saying. At this point in time, I've not seen any data, but I'm willing to kind of bet on the fact that I think my function is smooth. And that's a very interpretable thing to do at this point. Okay, so now let's suppose we have some data. Okay, so this is my data. So if we're going to write it out as a, keep losing this thing. In terms of Bayes' rule, we have this P of f. So this is my prior, basically. So for a given function, I can tell you how likely I think it is. And basically that's saying, you know, if the function is smooth, then it's probably quite likely. That's what that last slide was kind of showing you. And then what we do is we're interested in some term. So what would be the probability given that function? There is a denominator. We can ignore that. Let's just look at proportional to. And this is what we're interested in getting at the end. Okay, this is our posterior. Okay, so what's the probability of seeing this kind of particular function given that I've seen the data? Okay, so you see that a function that is very likely to according to our posterior has to be a function that both is likely according to our prior. So in our case, it would have to be a function that was nice and smooth, but also it has to be a function that gives you a high value of this weird sort of looking term here, which is basically saying what's the probability of seeing this data set given a particular function, okay? And when we're calculating this, you could think of this as like, does the line go through the data points? If it does go exactly through the data points, then that's great. We're going to get a very high score here. It's very likely that our data set was generated by that function. But by writing things like this, we can be very explicit as well about like how noise comes into everything, okay? So maybe there's a bit of noise in here. So we could say, okay, as long as the line is kind of quite close to the data, or maybe if the line is close to the data over here, but kind of gets worse towards the end, maybe that's still okay if we're in a noisy problem. So we can encode that information in here. But that's how it works. And then actually in practice, you can kind of calculate this stuff all in closed form and do nice maths and things. But let me kind of show you an example here. So here again, I'm just drawing all of these samples from our prior again. So you see that none of these really match up with the data very well, okay? But you can imagine now, if I were going to do an infinite number of these draws, so basically just plot all possible smooth functions, some of them are going to match up nicely with the data points, okay? So some of them are going to give me a nice high score here, whilst giving a nice high score here. So now what I'm going to do, so here I've plotted functions drawn from my prior, but now I can do the whole Bayes theorem here to get my posterior, and I can draw samples from my posterior. Okay, and that's the sort of thing we get. So these are the functions that are left. So imagine I'd sampled a very large set of functions before. The ones that are left are going to be the ones that kind of go nicely through the data, but are still very smooth, okay? So this is nice. And these are all kind of possible functions according to my posterior, okay? So this is very different, again, from standard machine learning, where you'd get kind of a single function. Here we have a really good understanding of like, okay, we think it's probably around here, but it's possible that actually, if we made predictions, we might be off by a certain amount. And the really nice thing is that you end up with kind of something that looks very similar to what you started with. So you kind of preserve these properties of smoothness. Another way of thinking about this as well, you can actually, if you're using these equations, you can still make kind of useful predictions that look more similar to what you get with a neural network, for example. So we can make a single kind of best prediction, which would represent the mean of our posterior. So the mean of the samples I just drew. So that's this red line here. But then we can also kind of summarize all the information we have about our uncertainty in the predictions, and that's these kind of uncertainty bands here. So you get all of that from these sort of frameworks as well. So you see this is kind of a really nice model. It's really flexible. It's able to kind of pick up the data that we want, but kind of crucially, because we've kind of been able to encode various aspects of what we think the function will look like, and also how much noise there is, you see it's not overfitting, right? Like if you fit a neural network to this and you didn't do anything crazy, you just get a super wiggly line that will just go through all of the data points, right? And it wouldn't be a good fit at all. So this is kind of a nice example here. So let's try something slightly different. Okay, so here I'm doing something else. This is called a Matern kernel. The details aren't particularly important, but this is another type of assumption I can make here. So now I'm saying, okay, I think my model is a Gaussian process with this different type of kernel, and this kernel is basically saying, I think my function is probably pretty smooth, but it's not going to be as smooth as the RBF. Maybe that's too unrealistic. So I'm assuming maybe that I can differentiate twice or something. So now we're seeing these sort of functions. These are the sort of functions that we think are likely to occur. Okay, so these are kind of qualitatively very different to the ones before. You see we've got kind of these jaggedy bits here. But for many kind of real-world processes, this is the sort of behavior we expect. And we can do exactly the same thing as before. So this is our prior, we fit it to the data, and when we sample from the data, we get these sort of functions. So I don't know if you remember from the slide before, they were much smoother looking functions. So you see here we have kind of like local wiggly bits, some kind of slightly more jaggedy bits. So if we know kind of our process is more likely to behave in this way, then we can very clearly kind of encode it in here. It would be impossible in the kind of the standard, in this sort of framework, even if you had a neural network with like 1 million weights, putting a prior on that forced all the functions that we kind of are considering to be, second order differentiable would be basically impossible. I don't know how you'd do that. Whereas here, there is kind of a nice framework to do it. And then I have kind of just 2 more examples. One is this Matern 3.2 kernel. So this is an even more kind of jaggedy function. So we're still assuming some notion of smoothness, but we're no longer kind of forcing this differentiability. So now you can imagine that I'm saying, okay, I think my function is kind of smooth, but I'm allowed some kind of discontinuities. So these are the sort of functions now that we're thinking of, right? So ones that look like this. And you might see this in kind of some sort of real-world stochastic process. You're trying to model kind of these kind of much more jaggedy jumps. So as I said before, these are the large set of possible functions. This is my prior. I'm saying I think that the function is probably something that looks a bit like this. You do your Bayesian inference, you update your prior to get your posterior from your data, and you see that these are now kind of the functions that remain, and this is what we think is going on. So we've still got this information, right? We've still been able to encode the fact that we think the function's a bit more jaggedy, and you see that here in these samples. So just as a final example here, so this is some really, really simple toy problem. So here I'm trying to do a forecasting task for some CO2 concentration data set. I can't really remember much of the details, to be honest. But imagine we were going to try and fit a straight line or any sort of line through this data, okay? So a neural network, maybe you kind of you do something like this. It looks like there's kind of steps, right? So that maybe you'd be able to pick that up. But actually, suppose I know that it's periodic, annually periodic, okay? How would I encode that into a neural network? It'd be very, very tricky, right? Or in like a linear model or something. If I say I want my function to be periodic with a certain periodicity, it's very tricky. But actually in a GP, there's a kernel, a choice of kernel where you can say, okay, I think my function is going to be periodic. And if you do that, you get this sort of thing. So again, this is kind of the best guess of what's going on is in the kind of the central bit, and then we have some uncertainty bands out there. So if we hadn't done anything Bayesian in this problem, right, if we just used a neural network or just a non-Bayesian regression algorithm, we probably would have learned something that was like this. But the fact that I'm able up front to go, okay, I know that this is going to have some sort of periodicity, like every year there's going to be temporal effects, I can just tell the model that, and we're able to learn this, right, with what it doesn't feel like enough data to pin it down. And that's really the key thing here, is that we can, by being very clever, not only can we get kind of better models, we can also really kind of reduce the amount of data that we need. So there's much more exciting examples here where you can actually encode some really cool physics stuff. So I'm going to show you all a couple of pictures from some interesting papers I found. So this kind of work isn't that well developed. There's lots of people working on it at the moment. I've got Ivan, who's over here. He's a summer student working with me, and we're kind of trying to include some of the things I'm about to show you in like a modern Python library so people can use them. But these are kind of really interesting ideas, I find. But there's kind of really cool stuff you can do. How do I escape this presentation? Maybe this is it forever now. Okay. This feels a bit controversial, just showing papers in a talk, but okay. Here we go, right. Let's suppose I'm trying to model some ocean data. So this is going to be like a vector field of the ocean flow. So this is going to be some sort of, we're going to get kind of hopefully a smooth field that's showing the way the ocean is moving. And actually, imagine I have a prior. My prior is that actually this function is going to satisfy some sort of like Helmholtz-like behavior, and actually you're going to be able to express this ocean flow as something that looks like a divergence and also a rotation. Okay, so this is a prior. I'm saying I think that this holds, right? This isn't something that we can pull out from the data set. This is something I'm adding in extra to the setup. And they have these really nice plots here. So they've got basically no data in this setting. Okay, so these red lines are the data they have. I think this is a toy problem. This is the data they have from some pretend drifter. And this is on the top left here is the ground truth. So this vortexy sort of motion is what is actually happening in their simulator. And they assume that they only see these red bits of data. Okay, if you were going to fit a very standard machine learning model, or even kind of a Gaussian process without anything clever going on, these are the sort of predictions you would get out of your model. Okay, so here all they've assumed is that the function is somehow smooth, and you see that they have this nice smoothness. But you see that this here is nothing like the one up there. Okay, but in the top right, they're able to kind of encode the prior that they think that the function is going to satisfy this Helmholtz decomposition, and you see that they're able to recover very much something that's very nice and looks very much like the function on the left there. Okay, so this is a type of prior, right? We're encoding some physics. This isn't something that they've pulled out from the data set. If all you use is the data set, so these red lines, you end up making predictions like this. But by including kind of much more interesting physics knowledge, we do much, much better. Let's look at this setting here. So for example now, imagine that I have some noisy data, and I'm trying to make predictions of a system in the future. Okay, so maybe I have something that looks a bit like this, and I'm trying to like estimate what the function theta is here. But I've got some noisy estimates of what's going on. But suppose I know that this function holds. So this could be some sort of prior, right? I'm saying I know some sort of physics that's going on, and this is very much going to constrain the sort of functions that I'm interested in. And if they do that, they can get much better predictions. So here, if we look at the top left here, so they've got these red dots. This is their data set, and they've tried to learn a predictive model going forward. So the black line is what they want to, that's the ground truth, that's what they should be getting, and the blue line is kind of what they predict using a very standard method with the uncertainty estimates in the blue. Okay, so they can see it's really not working. But if you instead encode the fact, so through your prior, you say, actually, I have this extra information, and this extra information is telling me that these functions have to satisfy that differential equation, you're able to get kind of much better predictions on the right there. So you see that we're able to kind of loosely kind of pin down the function, and actually, if you do things slightly different and even kind of more specific prior, you're able to get really, really good models here. So we've not got any more data. All that's changed is that we're encoding more information about what's going on. And I think this is a really compelling example. There's another nice one in this paper. Okay, so they have this function on the left here. So they have this is the background is kind of the ground truth of what's going on. So this is some sort of diffusion reaction system. They know some sort of differential equation that they think is probably happening in here. All they've collected are these blue dots here, okay? And they're able to say, if they just use these blue dots, the sort of predictions you make look a bit like this. Okay, however, if you're able to kind of say, actually, I think these differential equations are in play, so if you encode that information through your prior, you're able to get this plot on the right, which is much closer to the real world. And again, if you go with an even kind of slightly more specific prior, so encoding even more information, you get something else. And I have a final example. So this is different as well. So this is a prior here where they're able to say, okay, I'm going to try and learn some sort of surface, but my prior is that this surface is going to satisfy some sort of, for example, a diffusion. This is a heat equation, right? So they're saying, okay, I think my functions, but here functions aren't just kind of 2D things, they're 3D things. So they're kind of 2D and then also have a time element. So here they've got a time 0, time a half, time 1. And they're saying that whatever function I learn has to satisfy this heat equation. So it's kind of, and this is a sample of the possible functions they could learn. So this is kind of analogous to the plot I showed you where I drew all of the lines before I then fit them to the data. So there are ways to kind of encode really interesting bits of physics like this as well. But I think I'll stop there. I realize I haven't really explained what a Gaussian process is, but I felt like I couldn't really do it justice. So I just wanted to kind of touch on these ideas of why these Bayesian approaches are very different to what people often use in machine learning, and why we should be quite interested in them, I think, in climate science. We've got some examples, so once you've had your break and you come back, we've got some notebooks that people are going to run through. There's more maths in there if you are mathematically inclined. Might explain a little bit more of what's going on. But they're going to talk through some of, not examples quite as complicated as this, but some other examples of how do you encode various bits of knowledge in a machine learning algorithm, basically. But yeah, I'll leave it at that.